Okay, let's check the property of rotation matrices. Okay, as you know, the rotation matrix has the nine element, but the three element is independent. It means that we have the six constraint. So let's consider the constraint. The first one is the unit normal condition. It means that every column vector of the rotation matrix has the magnitude 1. So to be the unit vectors, the first one skew, the second one skew, and third one skew, and so all of the sum of this element will be the 1. Okay, it will be applied to the second column and the third column, and then we have the three constraints from the unit normal condition. And then every column vectors are orthogonal each other. It means we have the one constraint, one more, and two, so three. So we have the three constraints from the orthogonal constraint. So we have 6. So the remaining 3 elements, 3 variables will be independent from the rotation matrix. Those kind of 6 constraints, 6 conditions will be expressed more compactly as a single set of constraint, single set of equation on R. It will be written as R transpose R as an identity matrix. By using this equation, we can apply the 6 constraints, this one and this one. One more, we assume that all the reference frame is using the right-hand rule. So it can be expressed by using the mathematical description. If x times y producing the g, then the frame will be defined as a right-handed. On the other hand, if the x times y producing the minus g, it will be defined as a left hand. It can be expressed by using the mathematical notation, especially the determinant equation. Okay, if you determinant of the R matrix can be expressed by using this equation according to the definition of a determinant. In here, this part it will be the G. So the determinant can be obtained as a 1 if we are using the right-hand rule. On the other hand, we are using the left-hand rule, the determinant value will be obtained as a minus 1. So we can check the determinant of the rotation matrix. If you have 1, you are using the right-hand rule. On the other hand, left-hand rule is used. Okay, as a summary, we will introduce the 2 definition. Okay, the special orthogonal group denoted by the SO3, also known as the group of rotation matrix, is set of all 3 times 3 real matrix R satisfying 6 constraint and right-hand or left-hand rule. Okay, like this, by satisfying the 2 constraint, we can define the SO3 or SO2. SO2 implies 2-dimensional rotation matrix. Okay, in the case of the SO2 rotation matrix, maybe you are good at this kind of rotation matrix from the high school. Okay, so we will skip. Okay, let's consider the rotation matrix property. In order to explain it in mathematical way, we will introduce the group. Group is the mathematical rotation. Okay, the set of rotation matrix SO2 and the SO3 are called mathematical groups because they satisfy the property from the mathematical group 1. Okay, in order to define the group, mathematical group, we should consider the 4 kinds of condition. for given two elements in the group, the result, the multiplication, will be the element of the group. It means the result of the multiplication of the A and B also belonging to the same group. That is called as closure. The group is closed. Okay, result will be found in the same group. The second condition is associativity should be satisfied. Okay, so it does not mean the commutativity, just associativity should be satisfied for the group. The third element is identity element should exist for the group. In our case, in the rotational matrix group, the identity matrix exists. So we have this one, and the inverse element should exist. There exists an element A inverse in the group, such that A inverse A should be identity. Like this, A inverse can be found, then we can define the mathematical group. Okay, let's summary. The result will be the closed. Associativity should be satisfied. Identity element exists. Inverse can be found in the group. Like this kind of four conditions are satisfied, we can define the mathematical groups. Okay, especially in here, so SON, SO2 or SO3. Okay, the SON, n-dimensional SO groups are also called matrix Lie groups. Actually, this is not lie. It should be pronounced as a Lie. Okay, the Lie group is the SON groups in here. Okay, we have the four propositions here. The inverse of rotation matrix belonging to the SO3 also rotation matrix. So the inverse exists. It can be easily find out by using the transpose operation. Okay, we should memorize the rotation matrix inverse is equal to the transpose of rotation matrix. The second property, product of the two rotation matrix is also rotation matrix. Okay, the 2 times rotation will be another description of rotation. Okay, proposition 3.3, multiplication of rotation matrix is associative. It means R1, R2 operation is first performed, and then R3 multiplied later. The result will be the same as first multiplication of R2 and R3, and then later the R1 is multiplied. Like this, the associativity should be satisfied, but it is not guaranteed to be satisfied the commutativity. So in normal case, the commutative of R1 and R2 will not be equal to R2, R1. Okay, we should memorize in the mathematical group, associativity is more important, but commutativity is not considered in the performing the group operation. Okay, for any given vectors x belonging to R3, then the R, as you know, the R belonging to the SO3, the matrix vector operation Rx, the result will be the y. The y has the same length of the x because the R matrix has the normal unit magnitude of all column vector. Okay, the rotation matrix can be used with the 3 kind of laws. The first one, it can represent orientation. It can change the reference frame. it can rotate back to our frame. In the case of the second and third, it actualized operator, not description. So, okay, let's assume that there is a coordinate free point P. Let's attach coordinate frame X and Y according to the right-hand rule. G is defined. In here, the point. Let's assume that this is the unit 1, 1. So we have the 1, 1, 0. Is it right? Okay, the same point, but the frame is different. X and Y, G is defined. And we can get the point +1, -1, 0. So we have the PB. And at the same point, the X is defined like this, and the Y and the G. Then we can get the 0, -1, -1. Okay. In here, if the fixed space frame is aligned with the A, okay, the A is a space frame, then the rotation matrix of the A can be the identity because the same frame is aligned to the A. Okay, how about the B matrix? In here, XB can be led using the A frame. Okay, let's let it. This one is aligned to the y-axis, so this vector can be led 0, 1, 0. So we have the first column. Okay, let's lead the YB. This will be the -1, 0, 0. So we have the second column. I'm sorry. Okay, how about G-axis? G-axis is the same. So 0, 0, 1. Okay, let's lead the axis C in terms of the A frame. Okay, how about that? It will be equal to the G-axis 0. So this axis will be denoted by the 0, 0, 1. So we have this one. How about the Y? -1, 0, 0. How about that? This is 0, -1, 0. Like this, we can lead the orientation of the frame. Okay. Like this, we can express the orientation by using rotation matrix. Okay, in more explicit form, okay, in here we assumed that already the space frame is aligned to the S in the previous page. Okay, how about RSC to denote the left frame C of the second subscript relative to the S of the first subscript. Okay, for example, the RBC is the orientation of relative to the B. Okay, let's denote the RAC, orientation of the A, orientation of the C relative to A. So okay, let's read it. Orientation of the C in terms of the A, it can be led the 0, 0, 1. Okay, YC -1, 0, 0. Okay, this one 0, -1, 0. So we can read the RAC is reference frame C relative to frame A. Okay, let's read it again. Okay, in the case of the RCA, it means frame A relative to C in the inverse way. Let's read the XA in terms of the C frame. Let's read it. It will be equal to -y So 0, -1, 0. It will be the first column. And okay, the second one, YA, in terms of the C coordinate, it will be equal to the -G. So 0, 0, -1. Second column. How about third? ZA will be equal to the XC. So 1, 0, 0. Fortunately, by multiplying the two matrices RAC, RCA will be the identity. Okay. According to the mathematical group condition, the identity exists and the inverse also exists. It means RAC is equal to inverse of RCA. Proposition the 3.3, the R inverse can be expressed by the transpose. So RAC is equal to RCA transpose as an inverse. Actually, for given any frame D and E, RDE is equal to R inverse ED. It can be expressed by the transpose operator, R transpose ED. Okay, like this, we can express the orientation using the more explicit form. Orientation of something relative to the another reference frame. Okay. Orientation methods can be used to change the reference frame. So in here, RAB represents orientation of the frame B in terms of A. RBC represents orientation of the C in terms of B. Okay, let's multiply the both rotation matrix RAB and RBC. Okay, the latter part can be used for the description of the C frame in terms of the B. The front part can be interpreted as operator to act like reference frame from the B to A. Okay, RBC is just description of the rotation, and this part can be interpreted change reference frame from B to A. So this rotation can be expressed in terms of the reference frame B. It can be changed into A by using this operator. So we can describe the rotation matrix, and we can apply the operator here. Then we can get the change. We can get the changing the reference frame. Okay. This can be interpreted as this can be defined as a subscript cancellation rule. If we multiply the two matrices, the same frame appears both sides. It can be cancelled out each other. Then we can get the RAC. One more, the RAB is the description of rotation, and the PB is applied. Same B appears both sides. It can be changed into PA. It means it changes the reference frame. Is it right? Okay, the reference frame of the vector can be changed by a rotation matrix using the subscript cancellation rule. It's very good tool to reduce the number of subscript. Okay, third role of a rotation matrix is to rotate vector over frame. It's most important concept in this page. Okay, let's assume that we have the reference frame X and Y and G. Okay, let's assign the rotation axis omega hat and the rotation angle theta, just like a screw axis as a screw motion. Okay. Okay. In this case, we have the new coordinate C prime. Is it right? Because the rotation square axis movement will make the another description of frame. Okay, in here, rotation matrix is assigned as a RSC prime. Okay, the rotation of the C prime relative to space frame or fixed frame. If you know the unit vector of the direction of rotation axis and rotation angle or theta, then we can define the rotation matrix as a general form. Okay. Okay, this is obtained from the Rodriguez formula. It will be explained later. Okay, next section. Anyway, let's denote S theta for the sine theta, C theta for the cosine theta. Okay, in here, by using this kind of notation, we can derive the axis rotation amount of theta. Okay, let's apply. In here, the omega 1 hat is 1. The remaining parameter is 0 and 0. Okay, let's apply it. Okay, this is the 1. So we can get the 1. Okay, this is the 0. This is the 0. How about that? 0 and 0. This is the 0, 0, 0, 0. Okay, omega 2, 0, 2 square is 0, so cosine theta remained. This is the 0. The minus sine theta remained, 0. Sine theta remained, and 0. So cosine theta remained. We have this description here, right? This is rotation about x-axis. If you apply the 0, 1, 0, then you can get this y-directional rotation matrix. On the other hand, 0, 0, 1 is applied, then we can get the g-directional rotation matrix. So this equation, the Rodriguez formula, is the general form of rotation matrix for any direction of rotation axis. Okay, let's assume that in here omega hat is defined as a g-axis, and then rotation angle is the same as a 90 degree. So let's apply it. Then we can get the new description of a reference frame. Okay, for given this rotation matrix, let's apply another rotation, front side or back side, or pre-multiplication or post-multiplication. Okay, this is the space frame, this is the body frame attached to the center of mass of the rigid body in normal case. Okay, in here, let's multiply the rotation matrix. Rotation matrix acts like g-directional axis by an amount of the 90 degree. So the only difference between this one and this one, the position of location of rotation matrix. Okay, like this, pre-multiplication of rotation implies rotation of R in the reference frame. On the other hand, the post-multiplication of rotation implies rotation by the R in the P frame. Okay, I think it's better to memorize these two concepts. Okay, for given rotation matrix, another rotation matrix is applied to front side and the back side. The same notations are multiplied both ways. It means it it brings out R prime, it can be obtained by using the space frame rotation. Okay, the 90-degree one. Okay, pre-multiplication case. Okay, g-axis and the 90-degree rotation is applied. Actually, in the case of the body frame, xb is the same, so the rotation of the xb is required. Okay, so we have this equation. But the rotation axis is described in terms of the space frame. On the other hand, post multiplication, but this is described by the g direction by the 90-degree amount, 90-degree. Okay, let's apply it to this one. In that case, the body frame is chosen. Okay, the g-axis and then the 90-degree will be applied to here, so we can get another frame. Okay, the pre-multiplication and the post-multiplication will produce very different result. Okay, so the pre-multiplication will produce rotation by the R in the Laplace S frame. The post-multiplication implies the rotation by the R in the B frame. Okay, let's summarize again. Pre-multiplication by the R yields rotation about the axis considered to be in the fixed frame. That means S frame. Post-multiplication of the R produce a rotation about the axis, rotation axis, considered as being in the body frame. It means B. Okay, you should remember, you should memorize, you should mark in mind post-multiplication, the pre-multiplication and the post-multiplication. Pre-multiplication is about the space frame. The post-multiplication is about the base frame. Okay?